Right, students. So last we were discussing about dienes, alkadines. There was one reaction, one name reaction, which we didn't discuss, although it's not directly been asked in advance for a while now, but nevertheless, we will discuss this reaction. The name is Diels-Alder reaction, also termed as 4+2 cycloaddition reaction. Okay. These type of reactions are generally termed as pericyclic reactions. 1 minute. Yeah, right. So these type of reactions are called pericyclic reactions, where the reaction would happen something like this, where we have an conjugated diene treated with a double bond or a triple bond. On heating, it would give this. Got it? So both of them got joined, right, as a ring form here. This part, there are two reactant parts here. The one which has an conjugated diene, that is called as diene here. Sorry, diene. Got it? And the one on which it is attacking, the group which is attacking on diene, that is called dienophile. Just like electrophile, it is called dienophile, which means a species which likes the diene. Got it? So how does the reaction takes place here? So when you bring, alkadiene in front of any pi bond, then this pi which have been delocalized will start making a bond with this carbon, and the pi bond on the dienophile will start attacking on the diene form. So as it attacks, it establishes a transition state, something like this, where a bond is forming here a bond is forming this way, and double bond is losing out. So this type of a transition state is appeared. From there, the final product which is formed is double bond here. Clear on that, everyone? So we have diene and dienophile. Both of them react with each other to form this coupled product, and this reaction is called Diels-Alder reaction. Now, generally, how we need to look at it? In case if we have electron releasing groups in diene and electron withdrawing groups in dienophile favors this reaction. So for example, so in general, if we take, we have a diene here, plus this is a dienophile. Now dienophile may have a double bond or a triple bond. As long as there is a pi bond present, that is sufficient. Then there would be a formation of this product. Okay, let me take one more reactant like this. Suppose if diene is such that there is already a close ring on it, and again one more double bond is trying to approach it. Okay, so imagine it this way, that this particular ring which I have drawn, imagine as if this is that ring which has a double bond here and double bond here, that is being treated with this pi bond. So this pi will attack here, this pi will move, and this pi will attack on this side. So as it happens, what is the product? You can see 6-membered ring, and this side the attachment is happened this way. So I guess all of you got the point. Now the way to represent is also easy. Sometimes it can be represented this way, or if you take up a top view, these two carbons can be placed here also like this. Okay, this is the top view. So normally in top view, we'll make it a group like as if it is coming out. This is the product. So both way of writing is same. Another question, If you see, this is an alkyne on which we are treating with this double bond. This side, imagine there is a withdrawing group like CHO. Same thing would happen. The product form would be a connection here with double bond shifting and CHO. And this carbon, particularly, I'll just mark this carbon. So this is that carbon. This way you'll get the product. Like I said, we can show the same thing the way I have written here. 6-member ring with a group this way and a double bond with CHO. Now, one thing, if you observe commonly, this addition of this pi, addition of this pi bond is happening from the same side. So it is definitely a syn stereospecific. Secondly, the diene which is present is always in a cissoid form. Cissoid form as in, you can see both the dienes both are on the same side, not on the opposite side. This form is called a cissoid form. So what are the important notes we need to check is this is syn stereospecific addition. Secondly, the diene must be cissoid form. In case if it is a transferred form, reaction won't take place. For instance, if we have a diene this way, double bond is here, double bond is here, and I'm trying to treat that with a dienophile. This will not make any reaction. No reaction. Reason being, you can see this is a transferred form. And this bond is also restricted. We cannot move that bond or we cannot rotate that bond so that it can convert into a cissoid form. Hence, no reaction will take place here. Okay, everyone. I hope all of you have made a note up to this ABCD questions. This is the way it is. And imagine this carbon which I marked is this one. And there is one double bond here and double bond here, okay? On which there is an attack from this group. So this double bond will attack here, and this double bond will move as a conjugated double bond there, and the pi attacks from here. So what are we getting? Can you see it is leading to this molecule here? Right. Here there is CHO, butadiene, but in a transide form. And then imagine I'm treating that with a benzyne like this. See, dienophile could be anything. It could be even benzene also. Even benzene can attack that. Got it? So any form of dienophile, if it attacks here, now here this bond is not restricted. So it will immediately rotate and reaction will take place. Since there is no restricted bond, the minute this transferred form sees this, incoming dienophile, it would immediately change its orientation to become cissoid form. And in the cissoid form, now you can imagine it has turned into this form, and attack would happen such a way that this pi would attack here, this pi would migrate here, and the pi would attack here. So the product that would form here would be a double bond at this extreme and double bond this way, which is a benzene form. But imagine if the same diene is present, okay, in this transferred form with tert-butyl group on both sides. Tert-butyl group on both sides here. Now, tert-butyl groups are immensely bulky. Okay, so they are immensely bulky. So they won't be able to rotate and convert into the transferred form. Hence, here you will not see any reaction. So in the case of tert-butyl substituted, transferred forms, it would be very difficult to change into the cissoid form. Now, sometimes it would be mentioned that I took 2 moles of it. Suppose if you have 2 moles and we reacting that with quinone. This is the quinone. So from this end also it can make a Diels-Alder reaction. From this end also it can make a Diels-Alder reaction. So the product which we will get would be having, bicyclo on 2 sides. Here we have a double bond O with a bicyclo this way with double bond here. I guess that point is clear. So when you have 2 moles, this is how you need to check. Let's say this is the anthracene form which we have. And I'm treating this with a benzyne. This is a benzyne form. So benzyne form, we'll see where exactly is the cis-oid form. This side you can see it is a cis-oid form. So it would make an attack there. So we will have rest of the structure to be same here. Double bonds here, double bonds here. But from here, we will have a structure towards benzene. In case if we have a cis-oid form here and treat that with a dienophile which having 2 withdrawing groups like this, like cyanides. Now, like I told you, it is going to be a syn addition. It will happen on the same side. So this side, both cyanides will come outside the plane, or you can show them inside the plane. And since it is a mesoform, you will have only 1 compound. But in case if you have a transoid, this side, imagine we have a transform here, this way, CN and CN. So cis-oid plus transform here. Then this CN can come up, this can go down, or this can come up and this can go down. So we will have 2 products here, no? With CN out, CN in, or we can have CN in and this CN out. So what do we get, beta? Racemic mixture. Suppose in case when it comes to the di-in form, like I said, if you have any donating group, I'll write D as in donating group. And then we have a withdrawing group here, W as in withdrawing group. These are the most favorable conditions for reaction to happen, because donating group will always push the electron to initiate the reaction. So pi can attack from here, correct? And this pi bond will delocalize here momentarily in the transition state. If there is a withdrawing group, that will help it. And from there, it would attack here and this pi will shift here. This is how the mechanism usually takes place. So we would get a product with a cyclohexene with a product here with donating group here and withdrawing group here. So donating and withdrawing are, adjacent to each other. So we will get 1,2 product as major. 1,2 product as major. Got it? Also known as the ortho product. Because they are adjacent to each other, we'll get ortho product as major. Why I'm saying major? Because we might expect this also to happen, right? So because it is donating group here, and why am I not taking it this way? Withdrawing group is here, correct? So we can expect this to also happen, right? It can attack here, then this can attack here, and this could happen here. So we will get a double bond here with donating group here and withdrawing group here. So it is like the meta product, got it? Clear? So this type of a product is rarely seen, or this would be a minor product. Clear? So the major product would always be on the side where, the attacking species, will attack such a way the withdrawing group is on the opposite side so that it can facilitate this pi bond to move. Now, suppose in case if the donating group is here, donating species is here, I'll call it as D. And then the withdrawing species is here, W. Then if you see, if it is donating on this side, the pi bond would shift more onto this side, right? Because the pi bond cannot make a resonance towards this side. So hence, if you are expecting, this would be more formed here. So which means this pi will attack from here and this pi will attack from here. And therefore we'll have D here, double bond here, and a withdrawing group here. So how does it look like? Here we have like a para product, which is the major product. The other product would hardly be observed. Let me show you with an example. In case I have a diene with OMe, and OMe will undergo resonance stabilization to push these electrons away like this. So therefore, carb anion would be formed here, and that is where it would start attacking from. And we know that on the other side, if you have cyanide, let's say CN is there. So as it moves towards this side, the attack from here is more favorable, so that this pi can easily shift onto this side and cyanide would help to stabilize it. And that minus charge will attack here. The double bond will shift here. So what is the product we will get here now? Double bond here with cyanide and OCH3. So that's how OCH3 is helping to get para as the major product. Everyone make a note now. So when this is attacking now, beta, see how is it attacking? This would attack. As it attacks the cyanide, it can attack from the bottom or it can attack from the top. So cyanide can go in or cyanide can come out. Correct? At the same time, this pi has to attack here. Clear? So this can also attack from the bottom or from the top. So when it is attacking from the top, this CN can come up and this CN can go down either ways, because overall it has to be seen addition. Got it? So either way can happen. Let's see the preparation reactions here. So in case if you have N-hexane, this is N-hexane, and treat that with Al2O3, Cr2O3, right? Al2O3, Cr2O3, or we can use vanadium pentoxide, or we can use molybdenum trioxide, and heat, and heat, and heat. Then we shall get benzene. This is from simple alkanes. Now, within the alkanes, we will have straight alkanes also. We may have cyclic alkanes also. Especially from cyclohexane, we can prepare this reaction where we have cyclohexane reacting with all the above which I have written, like Al2O3, Cr2O3, and heat, and all of the same. This we can definitely get benzene. Not just that, now if you see, in case if I treat with platinum and heat, then also I will get benzene. I get this as benzene. We can heat that with sulfur or selenium and heat. This will also give us benzene. Correct? So these are all the reagents that can be used to get benzene from alkanes. No mechanisms for this. You just have to mug up how we get benzene from various forms. But when it comes to sulfur and selenium, at least one double bond should be primarily expected, Sc or S and heat. Okay, so one of the double bond is initially expected. So that is hexene. So in case if you have cyclohexene, then we can get this benzene form. From alkynes, we have already learned that if I take 3 moles of CH, triple bond CH, treat that in RHCT or RHFT, red hot copper tube, red hot iron tube, we will get benzene. This we have discussed yesterday. So in case if I take benzoic acid, COOH, and I treat that in the presence of NaOH and CaO and heat. Remember this is soda lime decarboxylation. So using soda lime decarboxylation, we will get benzene and CO2. Basically that will convert into Na2CO3 from halobenzene. So benzene with halogen present on it, and treat that with magnesium ether. So we'll get first RMGX and then do hydrolysis. So what do we get? We'll get benzene. See the mechanism. So halobenzene plus magnesium will first form phenyl magnesium chloride. That on hydrolysis, because this will have delta negative, this will have delta positive, it will extract proton from water and it will become benzene. Note that, everyone. It's a very special reaction. We'll come across this again in the chapter of phenols. Phenol, when you treat that with zinc dust and heat, this will immediately turn out to be benzene, and zinc will take away oxygen, becomes ZnO. So simple as a redox reaction is happening. Zinc is getting oxidized, benzene is getting reduced. Benzene with N2 plus and Cl minus. When you have presence of this and you treat with H3PO2, okay, or this is hypophosphorus acid. When you treat with hypophosphorus acid or ethanol, in both cases, they will act like a reducing agent, reduce this form into benzene, and this will get oxidized to become H3PO3, and this will get oxidized to form CH3CHO. Or so small fundamental, although you will come across this reaction almost like another 5-6 times throughout the organic chemistry now. See, generally when you have RNH2, now this could be alkyl or aryl, which means it will be with benzene ring or without benzene ring, as long as you have primary amine. Okay, as long as you have primary amine, you treat this with NaNO2 in the presence of dilute HCl. When you take NaNO2, sodium nitrite, add it to dilute HCl, it will convert into Rn2 plus and Cl minus. This is what it will change into. And this is called alkyl or aryl diazonium salt, diazonium chloride salt. Generally, alkyl are highly unstable. If it is aryl, it is stable, in less than 5 degrees centigrade. So from there, if you treat that with, H3PO2, something like this, what we have seen, this will get it as RH form. Okay. And it is more likely to make a reaction with aryl, so that's why I'm more interested in saying this with aryl. See, next, from benzene sulfonic acid. So in case if you have benzene sulfonic acid, how we can get benzene, let's see. So if you have SO3H, and in case if at all I treat that with dilute HCl, or if I treat with dilute H2SO4 or H plus and steam, okay, H plus and steam, it will convert into benzene, releasing out SO3 gas. On the other hand, this reaction is actually reversible, and you can react benzene with SO3 in the presence of concentrated H2SO4 to regain, benzene sulfonic acid. So this would become a reactions of benzene also, preparations of benzene also. Clear, everybody? Let us see the mechanism. So benzene sulfonic acid in dilute solution will make 100% dissociation. So we would have this O minus form here, and this is the way the ion would look like. And in the presence of H plus, if you have in the presence of H plus, let me write this double bond on this side, it makes it easier to show. So this pi bond will attack on H plus to extract that H plus. As it extracts the H plus, now we would have H on one side, S, double bond O, and O minus on the other side, with positive charge coming on this carbon, and double bonds will be present this way. From here, observe it carefully that this bond will be closing at SO3, and this bond is going to break and come here as double bond, that is retaining its aromaticity. So it will retain its aromaticity and becomes benzene this way, with this hydrogen that has come up with SO3. So that's how it happens in dilute HCl or dilute H2SO4. Steam is best used here instead of these three. If you see, H plus and steam is best used so that you can effuse out SO3. So SO3 can come out as gas. So if you ask like what is the best way possible, then H plus and steam is best. Done, everyone? Right. So these are the methods or preparation ways for benzene. This week's syllabus would be mostly up to this point only. Okay, everyone? So up to the preparation of benzene. Now, what we'll see is the substitution reactions. Substitution reactions on benzene. So in 11th standard, the substitution reaction is only about electrophilic substitution. Electrophilic substitution. So in 12th standard, we'll study about the nucleophilic substitution as well. So in benzene, if we bring across an electrophile and a nucleophile, electrophile will have more reactivity than nucleophile. Electrophile will get connected here, correct? And H will be loosed out with nucleophile. So this is the general reaction that takes place. And this type of a reaction is called as SAR, substitution AR and E, which means electrophilic. So substitution, aromatic, and here we are studying electrophilic substitution, so that's why it is called as E. Okay. This can also be written in different books, different format, ARSE. Means it is aromatic electrophilic substitution. Okay, let's see the mechanism now. Mechanism happens in 3 steps, dear. So step 1, first step is about generation, that is generating electrophile, generation of an electrophile. Suppose if you have E and U connected to each other, and it has to generate an electrophile this way by breaking the bond. This is step 1. Step 2 is electrophilic attack. Electrophilic attack. If we check the benzene would attack on the electrophile which was generated from the pi cloud. So think this way, benzene will only have electron rich surface, isn't it or not? See, when it comes to benzene, all of this, cloud that has been forming here, these are all the orbitals which benzene has, parallel orbitals, and the entire cloud is moving up and down this way. So there is a complete defense of electrons from the surface and from the bottom here, which means benzene is treated like an electron rich planar molecule. So it usually don't accept nucleophiles, because nucleophiles will also come with electron density. But when an electrophile approaches, the pi bond has, one of the pi bonds can have the attack on the electrophile observed. Yes, so I think that makes sense why it is going for electrophilic attack. So it will attack here, and this is the slow step or the rate determining step. So as it forms here, this would have a connection here as double bond here, and E can be attacked on either of the side. I'll just put it here with positive charge. Got it? But you can see this positive charge can be moved onto all the different locations here. It can move onto all the different locations. So while attacking, it is going through a transition state like this. So this is the entire cloud. And this cloud is making an attack to electrophile with delta positive, right? This is the transition state that it is going through. Representation of this transition state is called pi complex. This is a representation known as pi complex that the benzene is attacking. And once it has formed a bond, after bond formation, now it has one hydrogen. This carbon has already one hydrogen is present on this carbon. On that carbon, now an electrophile also got added up. Okay. So since a sigma bond has been formed in here, this is also known as sigma complex. This formation is called sigma complex. So the transition is known as pi complex, but the intermediate which has formed is called the sigma complex. So this sigma complex has various names. It is also known as arrhenium complex, or any arrhenium intermediate or arrhenium complex, or is also known as valent complex, named after the scientist who has come up with the mechanism, intermediate. Valent complex or valent intermediate. Clear, everyone? This is the second step. So the attack of electrophile is the second step. Now you can see that the sigma complex has resonance stabilization here. It has H and E with positive charge here, and if this pi can move here, it would undergo resonance stabilization with plus here, double bond, and H and E here. And if this pi moves here, we'll get positive charge, double bond with H and E here. You can write H and E either ways. If you check out the hybrid looks this way, where we have H and E here, and from this side towards this side, positive charges run. So this is a representation of sigma complex or valent complex or arrhenium complex. No, that's why I have not written the complete circle. Positive charge which I have written is in this way, or you can show it here also. Doesn't matter. Then this is the second step. Now see the third step. So third step is about retaining the aromaticity. So that is regaining aromaticity. Let me write this as step 3. So what we got here is this complex with H and E with positive charge. Right. Now the nucleophile which is present in the solution will extract this proton, thereby again the double bond will close. So what we would have here, is this electrophile, okay, with double bond, this plus Nu and H bond has been formed. So eventually what happened, hydrogen has lost, electrophile has substituted there, correct? So that's why it is a substitution reaction. But the substitution is happening in 2 steps, right? First an addition is happening, then an elimination is happening. So we can say that, note, ArSE is an addition, elimination mechanism. Overall, it is undergoing substitution, but through addition and then elimination is happening. What you are asking is an addition product. Suppose if an electrophile is here, nucleophile is here, it is losing out its aromaticity permanently, which is an unstable form as compared to that of benzene form. Got it? So this product is never going to form. Everyone has made a note on this. Now let us see how the reaction progress graph looks like. Now we started off somewhere here with benzene, and on benzene an electrophile started attaching on it. So from here it reached to, an intermediate form here. This is an intermediate form. So from this intermediate form, through a small transition state, it has reached to a new place where it is more stable. Correct. So this is the way it has been happening. Now if you see the first step where the electrophile getting added up is the highest activation energy, which means the slow step. Right. So what is the transition state that has taken place here? See how the transition state is. Okay, let me just write it as TS1 here. TS1, TS2. And what is the complex that has formed? This is valent complex, H and E with this positive charge. This is a valent complex that has formed. Let me show what are the transition states here. So transition state 1, how does it look like? We have benzene with double bond here. This bond is getting broken. Hydrogen bond is intact, but a new bond is made with an electrophile. And the positive charge is shifting here. This is transition state 1. Transition state 2 is the way the bonds are. Okay. This new bond is forming. Hydrogen bonding is lost. Electrophile got attached to it. The delta positive charge is here and hydrogen is losing like an H+. This is transition state. I guess this point is clear, everyone. So this is energy versus reaction progress. So what is the final product we got? Final product we got is electrophile here.
So the energy on the y-axis we have taken also. It is only of the prime compound benzene only.
Yes, beta. Benzene, how it is changing to this.
But not of the E plus or
no.
Other compounds.
We always write reaction coordinates for reactant. Now the important thing to note here is in most of the reactions, in fact in mostly all reactions which happen through this substitution, what we call it as electrophilic aromatic substitution or ARSE, no kinetic, isotopic, no kinetic isotopic effect is observed as rate determining step does not involve breaking of carbon hydrogen bond. In most of the cases, this is what we'll observe, that there is no kinetic isotopic effect, which means even if you put hydrogen or deuterium, the rate would be almost the same. So which means rate of C6H6 will be same as C6D6 will be same as C6T6. So rate of electrophilic substitution will be same in all three cases. In most of the reactions, however, reactions in which, keep writing with me, however, reactions in which energy difference between transition state 1 and transition state 2 is negligible, then kinetic isotopic effect is observed. But what are the best examples? Iodination, sulfonation, right? In these two cases, we would usually see the rate is slightly different, which means now the rate of the reaction would be C6H6 better than C6D6 better than C6T6. To retain aromaticity, hydrogen is being removed, correct? Now, general cases is that in case of general electrophilic aromatic substitution, this activation energy is very less, where I'm pointing out. Okay, but in the case of sulfonation and iodination, that activation will be more, which means it is quite comparable as compared to this activation now. Understood? So in that cases, we will see there would be change in the rate. Okay, so what I meant to say here, although the first step is not, if you check out the first step is definitely not different. It is the same. Till this point, it is same. So from here, for iodination and sulfonation, the peak may be slightly bigger, like this. Unlike the case here, you can check out. So now the transition state 2, as compared to that of transition state 1, will have more energy. Clear on that? Why this happens? See, the idea is why this happens, right? Check. When it comes to iodine, suppose if iodine got substituted here, positive charge is here, double bond, this, iodine and H. It may so happen that when you have weak bases, especially when you are using iodine, okay, the other I minus which is present in the solution, you know, whatever that has been substituted, here, this probability of breaking iodine and again getting back to resonance, or probability of breaking hydrogen and getting back to resonance is almost the same, because iodine bond length is itself very long. Understood? While hydrogen, it would also like to break because it wants to retain the aromaticity. Hydrogen can also be broken because it is not very strongly bonded with benzene. Clear? So when the dilemma comes in these cases where iodination and sulfonation, they are very weakly bonded to benzene, then the rate will be different in case if you take deuterium or tritium. Because now if the deuterium is present instead of hydrogen, now it becomes even more difficult because hydrogen bond, protium is easier to break compared to that of deuterium compared to that of tritium. That's why there is a difference in the rate seen. I hope the point is clear.
Yes, sir. So only these two cases?
Only these two cases. Only these two cases. The rest all cases you will take it as same rate. Okay. Ideally still the first step beta, because this activation energy may be still longer. But the second step would change the slight rate here because of secondary isotopic effect. Remember secondary isotopic effect? Primary means in the rate determining step. Secondary means not in the rate determining step. Well, hyperconjugation is not present here, okay, because that hydrogen is already sp2 connected carbon. It is two sp2 connected carbon. Correct? But C and H bond is relatively weaker as compared to C and D bond. Hydrogen, deuterium, tritium, all of them will be removed at almost similar rates.
Due to energy factor as well.
Because the second step would be less energy required, correct?
Yes.
Clear? So that is hardly accounted for the overall rate. Understood? But here for the overall rate, this will get accounted. This probably is the most important part of organic chemistry. The most asked also in JEE. What are all the EAS type of reactions? 90% of the reactions in benzene are only EAS. Okay. So learn it carefully. So first, halogenation. Benzene, when you treat with X2, where X could be chlorine or bromine, then in the presence of any Lewis acid, right, like AlCl3 or FeCl3 or even simply iron, you can take, all of this will be acting as Lewis acids. So in the presence of a Lewis acid, we will get the product as halo substituted benzene plus HX. This is the reaction that will take place. Let us see the mechanism. Suppose if I take chlorine, Cl2 structure is Cl bonded this way. Now Cl has both sides, chlorine has 3 lone pairs on them. And when you treat that with AlCl3, which has an empty orbital, aluminium will have an empty orbital. So the lone pair will donate it to aluminium. So this chlorine will act like a base, Lewis base. AlCl3 will act like a Lewis acid. And you will see this bond gets polarized, which means chlorine originally were not polarized. But now since chlorine has donated the other side, this will start getting delta positive. And here, this aluminium, which is AlCl3, will start getting delta negative. This is the kind of transition state that is established. So now we get a polarized halogen. We'll get a polarized halogen. So as you can see, the minute polarized halogen is present, benzene will try to attack it because it would have an electron cloud on it. So Cl connected to Cl connected to AlCl3 with delta negative, delta positive. This bond will connect here. And this is, you know, that first electrophilic substitution itself is the slow step. So you'll get a positive charge here. Sorry, I'll get a positive charge here. Double bond with chlorine. So as soon as the chlorine gets attached here, it also has one hydrogen on it. So then this bond will break towards this other chlorine. So we will get this as AlCl4 minus. Now this is step 1. Step 2 is that this benzene, which has hydrogen and chlorine here. So let me put chlorine above, Cl and H here with positive charge. The relieved AlCl3, you know, with minus charge on it this way, right? Aluminium has minus charge, yeah. So what would happen? It will break this bond and try to extract proton from here so that it can retain its aromaticity. So hydrogen will lose the bond, try to retain its aromaticity. So it will retain its aromaticity, getting chlorine here, and HCl is formed, and AlCl3 will be formed here. This is the final product. Clear on that? So that's how we will get chlorobenzene, HCl, and AlCl3. So you can see AlCl3 is only acting like a catalyst here. Right. So practice that once again with bromine. As much practice you can do, that is better in this area. So do that once again, students. Suppose I'll give you the overall reaction. Second reaction. Let me put this as the first reaction. Second reaction. So benzene, if we have to react with Br2 in the presence of FeBr3. So how will you proceed it? Overall reaction, you know what it is. You get bromine here with HBr with FeBr3. This is the overall reaction. Write the mechanism, everyone, just for the sake of practice, everyone. Without seeing, just try to write all the steps exactly the way we have done it for chlorine. In case of Br or Cl, either ways, right? Both are carrying lone pairs, correct? Now, if you remember, non-classicals are mostly favorable when there is no resonance. But here, there are two double bonds adjacent to each other, correct? And they can undergo resonance stabilization. So this bond won't be present as a cyclic form. It will keep moving, you know. Clear, beta? Non-classical is most favorable when you have a localized double bond and there is no resonance after that. Now, if you have seen, I have only used chlorine and bromine in the cases. I didn't use iodine. The reason for it is iodination is actually reversible. Chlorination and bromination will happen mostly in the forward direction. But in case of iodination, it is going to be a reversible reaction. So let me mention that iodination is reversible. Iodination is reversible, and hence is done in presence of oxidizing agents. Oxidizing agents only. See, what does this mean? If you check out the overall reaction, suppose if you treat that with iodine, and forward reaction rate constant is K1, backward reaction rate constant, I'm writing it as K inverse or K minus 1. K minus 1 means back. This here, what would happen? Iodine will get added, H will come here, positive charge will form here. Let's say this is how we have it. I think this has double bond on this side. Okay, easier to understand. Now, the I minus which is formed here, got it, will extract this proton. Okay, and try to, what we are expecting is that this bond will break and close it as double bond, so that aromaticity can be retained. Iodine will get substituted, HI is formed. But this reaction will again happen in the backward direction. So if for this reaction, if at all I write the rate as K2, got it? So what has been observed, if you see, this is a forward reaction constant, backward reaction constant. Here this is a forward reaction constant. Okay, so it has been observed that K inverse reaction constant is greater than that of K2, which means, so the second step is mostly RDS here. Got it? If you see, that is why we are seeing the rate is, largely decreasing here. If you check out, we have seen it here, right? So when it comes to this step, the second step is becoming much more difficult to achieve. So that is where the rate will be completely decided. So second step will become the RDS here, and hence if you check out the rate now, C6H6 will be better rate than C6D6 than C6D6. Clear? So what we have to do, in case if this K2 has to be more favorable and the reaction should not drive in the backward direction, then you remove this HI. Okay, because it is an equilibrium reaction. If you can remove this HI and convert this HI back to I2, so product is lost, reactant is gained. So again, reaction according to Lee-Shatler's principle, again it will go in the forward direction. So basically what we will do, whatever the HI content, any amount of small HI that is formed, we will let it react with an oxidizing agent and convert that into an I2 form plus H2O. So thereby it will get a push of reaction more in the forward direction. Correct? Everybody understood this point? Now, what are these oxidizing agents? Oxidizing agents which we can use are HNO3, right? HiO3. We can use H2O2 peroxide. We can use HGO. All this can act like a source of oxidizing agent. The other reasonable way by which we can get iodomenzene is direct iodination. Direct iodination can be done by using interhalogen compounds. Interhalogen compound. Like, if you check out, like ICl. If in case if at all I take ICl in presence of AlCl3, which will act like a source of Lewis acid. So for example, if at all I take benzene, treat that with ICl, instead of I2, I'll treat that with ICl in the presence of ZnCl2 or AlCl3. I can take anything, ZnCl2 or AlCl3. So here we will get iodine to get electrophilic substitution, and HCl will be left. Which is more electronegative between iodine and chlorine? Chlorine, right? Chlorine, so chlorine will get negative charge, iodine will get positive charge. This is an electrophilic substitution. Who will get substituted? Where? Here? No, because it already got charged, delta minus and delta plus. Now this has less tendency to donate electrons as compared to that of chlorine. In case if you want to get halogen to be substituted, any halogen except fluorine, that is halogenation, may also be done using following reagents. First, suppose if at all I take Br2 in CCl4, or I can take Br2 in CS2. I can do this. Second, we can use X2. X here is chlorine, bromine, or iodine. X2 in water, H2O. You know that we have done this in alkenes, X2 and water. Or directly it could be given as HOX acid, HOX in H plus in acidic conditions. So all of these conditions are favorable. Again, X here is chlorine, bromine, and iodine. Favorable for halogenate. Bromine will get attached there because there is a pi bond delocalization which can happen, right? So it would exhibit mostly positive charge. If we have two double bonds here and bromine got substituted here, imagine bromine got substituted here. Positive charge is here. So this positive charge is continuously getting delocalized now. So to exhibit this delocalization and increase its stability, it won't try to be in a non-classical way. If it is in this non-classical way, then the positive charge will be concentrated only in this space. But if it is moving, it can exhibit that positive charge to migrate on all the carbons. So which is more favorable? This one is more favorable, not the cyclic form. So we'll stop it here for today. So tomorrow we'll discuss the rest of the ES. We have only ES for this week and next week. So you can imagine the number of reactions we'll get. Got it. So we'll take it very slowly because this is very important area. Got it. So tomorrow we'll discuss the nitration sulfonation cases.